All right, everybody. Time for another video, and as you could probably expect with the videos, this one will depend on you understanding some things that came up in the videos before this, but perhaps this one more than the others. Okay, so I'm not gonna re-explain certain things. I'll have to say if there's something in this video that sounds a little familiar, but you may not have understood completely, then either ask me about it or go look at some of the videos I posted within the last week. Okay, so in this video, we'll talk about something called the tangent line to a curve. And for the most part, I'll make this video be just the instructions for how to generate this thing called a tangent line to a curve. But there is some preliminary information. Okay, so here's the preliminary information, the facts that will depend on in order to go through the process that I eventually show you. The first fact I want to talk about is the slope of a line. Now, this would be something that you've heard of before, but quick reminder about it. If you have a perfectly straight line and you were to select any 2 points on the line and measure the run, measure the rise, and divide them, that's the slope. Okay, it really is that simple. As far as like different kinds of slopes, then if a line was going up to the right, it would have a positive slope, positive number, that is. And if a line was going down and to the right, it would have a negative slope, a negative number. Like when you calculate this number, it'd be negative, that is. And the bigger the number, the steeper the line is, either in the positive or negative direction. Okay, the least steep of all lines, a horizontal line, has a slope of 0, and that is because the rise on a horizontal line is 0, and 0 divided by whatever the run is going to be 0. Okay, so slope can be positive, negative, or 0 depending on if the line is going up or down or is flat. Okay, next thing is what will we be starting with? Okay, or what will we have to work with? Two things. F of x is a function or a curve. I might call it a curve sometimes because I just want to emphasize that in some cases we may be talking specifically about the graph, but what the equation and the graph are the same thing. The graph is just a picture of the equation, I guess you could say. So f of x is the function, if you want to think of it as just a formula, or the curve if you want to think of it as the graph. And f prime, okay, that's something mentioned in a video I just made yesterday, calculates the instantaneous rate of change. Again, topic from prior videos. But it will also tell you the slope of a curve, which is something I mentioned a little bit about in the video I made just yesterday. Okay, so f of x is a function or curve. F prime, the derivative, that was my other term that I had for it. Whoops. The derivative tells you the slope of a curve at a point. Okay. Well, one thing, like real quick, because it sound a little strange perhaps if we talk about that a line can have a slope. All right, a perfectly straight line, measure the run, measure the rise, divide them, that's the slope. But how could like something that's curved have a shape? Well, it's not that hard to explain, so I'll show you. So let's see, let's do like over here. Okay, so this is curved, okay? It is not straight, right? But it's kind of an illusion. Whoops. Anything that is curved, you could say, is made up of a bunch of like extremely tiny straight segments of line. So yeah, that is curved, but I mean, if we were looking at it on a microscopic scale, then it would look straight, okay? Or another way you can think about this is that if the Earth were a perfect sphere, then because it's so large and our perspective on the Earth is so small by comparison, it might look flat from our vantage point, okay? Or it would look flat. I mean, that's just how it would be. And even though the Earth's not a perfect sphere, you can kind of see how that would be if it was. So it's sort of like that, and we could say like, well, okay, yeah, a curve could have a slope. Like right here, it's not that steep, but yeah, I could measure the rise and the run on that little piece of a line, and I could tell you what the slope was. And like up here, it gets considerably more steep. But at every little part, every point on that line, you could imagine the nearby piece of it to be a straight line and has a slope. So, I could tell you the slope here, and it's going to be a line like so. I could tell you the slope here, and it's going to be a line like so. Yes, so okay. F of x is the function or curve. F prime measures the slope of the curve at any point that you want to measure. All right. So third fact, the equation of a line. So this is something I'll be taking for granted later on in the video, but the equation of a line is y equals mx plus b. So if I had a straight line on a graph, it would have an equation, y equals mx plus b. M is the slope of that line, and b is the y-intercept. B is the spot, the number where it hits the y-axis, okay? Last thing, the ultimate objective of the video is to derive the tangent line to a curve, okay? So I'll just tell you in concept what that is. Imagine you have a curve. All right, there it is. The graph of a function, and it's curved. It's not straight. The tangent line to a curve is a line that meets the curve at a specific point, and it matches the slope of the curve at that point. So if you can imagine zooming in on this curve right here, you wouldn't see two things. You just see one. When we zoom out, I see the curve and I see the line. I see two different things. But imagine if we were to look at a microscopic scale at that point, we wouldn't see two different things. The line and the curve would kind of blend together. That's what it means as the tangent line meets the curve at the point and matches its slope, okay? Just meeting the curve at the point isn't enough, because I could say, well, here's a curve right here, and then let's see, here's a point on it, and I'm going to do like this. There's a line that meets the curve at the point, but it's not tangent to it. It doesn't match the slope of the curve. No matter how much you zoom in on that, you'll see like the line and the curve kind of going at odds with each other, okay? So this would be not tangent. Okay, so those are all the concepts that we need for the video. Let's try to do a problem. So first problem, it's kind of a warm-up. Say that we're given information like this. F of x, that's the curve, is 1 over x. F prime, that's the derivative, that's the thing that measures the slope of the curve, okay? So this is going to tell me the slope of this at whatever point I would want to measure it. Calculate the slope of the curve at the point where x is 2. Okay, well, this is really easy to do. If you already have the derivative, if you already have the equation for the thing that measures the slope of the curve, you just put the x coordinate of the point into that, right? So if f prime measures the slope of the curve and you want to know what it is at 2, you plug in 2, you calculate f prime at 2, and that's equal to negative 1 over 2 squared. That's negative 1 over 4. Okay, so that part's not hard to do. Now, if you had to figure out what the derivative was, in addition to all this, that would be a little bit different. And for test 1, we're going to do like this. We're going to say f prime x is limit h goes to 0, f of x plus h minus f of x over h, right? So that's what we're going to do for test 1. There's other ways that you can find f prime. There are rules, there are shortcuts. You can use technology, calculators, right? But for test 1, then that's how we'll do it. All right. So yes, but once you have that, we can plug in the x coordinate of the point we're interested in, and it tells us the slope at that point. Now, some people are visual. They learn best by seeing things. So here I just told you what to do, but I'd like to show you in addition. So here's the graph. So I took my time and I drew this as accurately as I could. Okay, so this curve that kind of goes like that, that's the curve f of x is equal to 1 over x. Okay, and then right here is the point where x is equal to 2. Now, here's what we're saying. If f prime at 2 is negative 1 over 4, then we're just saying that this little section of that curve is like a line as you see here, where you go down 1 and over 4. Okay, that's what a slope of negative 1 over 4 would be like, down 1 over 4. So, if you could zoom in on this curve right there at that point, zoom in so close that the curve no longer looks curved, it begins to look straight. Remember, like the Earth is such a massive sphere that it looks flat from our tiny vantage point on it, like that. Then we would see a line oriented like this, slanted such that we have to go down 1 and over 4 to get from point to point on it. All right. Okay, now you can say, well, if it's so small, how could you go down 1 over 4? Maybe 4 seems like a lot. Well, this is by like any measurement. It could be like down 1 micrometer over 4 micrometers, like, because when you find the slope of a line, any 2 points will do. All right, so that's some context for the meaning of this number. Now, let's try something else. Suppose we have something like this. We have a function and its derivative. And now I'd like to find the equation of the tangent line to the curve at the point where x is 2. Okay, now again, if you're visual, think of it like this. In black, you'll see the curve. And in red, you'll see the tangent line that meets the curve at the point where x is 2. Okay, there's the point where x is 2. So those are the three things you have. You have the curve, we have the point, and we want the tangent line. Okay, so can we do that? That's enough information to do it. Can we do it though? So I'll show you how to do it, but before I get into it, I'll say this. The way I phrased the question is if you could find the equation of the tangent line to the curve at the point where x is 2. Well, if we're on the curve, a point has an x and a y coordinate, right? That's the way it works. And we find the y coordinate by saying 1 over the x coordinate. That's the equation that would generate the points and the curve as a result. So if you tell me we're interested in the point where x is 2, then there is a y coordinate with that point, and it'd be 1 over 2, so the y coordinate's a half. And I'll need that here in a minute. Now here's the process. Okay, here's how we find the equation of the tangent line to the curve. Step 1, I'll tell you the form that our answer takes. Y equals mx plus b. Why is the equation of the tangent line going to be y equals mx plus b? Well, because that's just the equation of a line at all. Anywhere. That's just how they work. This is the equation of a line. No matter if you're finding the tangent line or some line somewhere else. All right, so the answer has to look like that. Okay, now what were those numbers? Y equals mx plus b, what were the numbers there? Well, m was the slope and b was the y-intercept. Now, don't we already know the slope? What is the slope of the curve at this point? Well, the derivative tells you that. And in this problem, we found that for that curve, the slope of that curve at the point where x is 2 is negative 1 over 4. Okay, so the slope is negative 1 over 4. So like as a partial answer, this is not totally done, but I'm halfway there. This is a partial answer. Okay, that the answer must be y equals negative 1/4 x plus b, where I don't know the b, and now I'm going to find the b. Okay, so step 3, how do you find for b? How do you figure out what b is? Well, you see how the tangent line and the curve meet each other at that point. That point is on both the curve and the tangent line. So that would mean that if you plug this point in, x and y, into the equation for the curve, it would work. But it also means if you took this point, x and y, and plugged it into the tangent line equation, it would also work. That's how we'll solve for b. So my unknown point is 2 for x, 1/2 for y. Okay? And that has to work properly in the equation of the tangent line because it's on the tangent line. So let's say 1/2 for y. Y equals -1/4 x. So x is 2 plus b, and this is just enough information to solve for b. I got 1/2 equals -1/4 times 2 plus b. Okay, so 1/2 here, what's -1/4 times 2? That's going to be -1/2. And then I get plus b. And then if I were to add 1/2 to each side of this equation, I would get that b is equal to 1, right? Because it'd be 1/2, and then I'm plus 1/2. 2 halves, that's 1. So b is equal to 1. So that's my answer. The tangent line is y equals -1/4 x plus 1. Okay. So then I'm done. I found it. That's the equation of this line. If I had a graphing calculator, or if I could generate the graph somehow, and I plotted this and I plotted that, you'd find them meeting like I have it here at that spot. Okay? So you can check your answer. If you graph both this and your answer and they didn't intersect, or they intersected in some different way, then it wouldn't be right. Okay. Now let's try one all the way through. Okay, so given similar information this time, I have a curve g of x and its derivative g prime of x, and g prime tells you the slope of g wherever you want to look. And I'm going to find the equation of the tangent line to this curve at the point where x is equal to 9. If you're visual and you want to see what that looks like, here's the point. 9 for x, 6 for y. How did I get that? Well, if I put 9 into the equation for that function, it says 2 root 9. Root 9 is 3. 2 times 3 is 6. So that's the point. So the point might say x is equal to 9, but we're going to need both the x coordinate and the y coordinate. Okay? So, okay, it says 9, but it's really like 9 for x, 6 for y. All right, so I've got that. Here's the curve. And again, I tried to very carefully draw this graph accurately the way it really looks. In black, you're seeing it. And in red, that's the tangent line that meets the curve at that point. And again, you can imagine if you looked really close right there, you wouldn't see two things. You wouldn't see the tangent line and the curve. They would blend together. All right, so let's go through those steps. Let's, well, maybe I think I can do it right over here. So let's say, here I'm going to do the steps in the same way that I showed you. Okay, so step 1, my answer takes the form y equals mx plus b, because a tangent line is a line, and that's the equation of a line. Okay, and step 2, well, m's the slope and b's the y-intercept, and I have something that tells me the slope. So I want to find the slope of both the curve and the tangent line at the point where, hold on a second, there we go, at the point where x is equal to 9. So I put 9, the x coordinate of the point that I'm interested in, into the derivative. That's going to be 1 over square root of 9. Square root of 9 is 3, so that's going to be 1 over 3. So the slope of my tangent line is 1 over 3. Okay, so this is my partial answer. It's 50% of the answer. Y equals 1 over 3x plus b. Okay, and the third step, well, I have to find out what b is, okay? Because my equation will have y and x as variables, I'll have to figure out what m and b are. So I'll use my known point, okay? So my known point is 9 and 6. That's a point that's both on the curve and on the tangent line. So the x being 9 and y being 6 got to work, okay? So let's see, 6 for y, 9 for x, and that's just enough information to solve for b, okay? So I got 6 equals 1/3 times 9 plus b. So 1/3 of 9 is 3. So I get like this. Say I subtract 3 from both sides, I'll get b is equal to 3. Okay, so b is equal to 3. That gives me my full answer. The equation of the tangent line, that line right there, y equals 1/3 x plus 3. Whoops. Plus 3. Okay. So that's how we can find the equation of the tangent line. I won't include, at least now, any applications of this in the assignment, but for now, this is how we'll find it. And if we use it later for something, at least we know how to find it. Okay. So let's look at one last thing that relates to some of the other information I put at the beginning slide up there. So this one is not a problem to find the equation of the tangent line or anything like that, but it's an example on understanding if we can grasp what the derivative tells us about the curve. Okay, so it says this. So I got two graphs, choice A, choice B. Okay, and it says choose the graph of the function f of x such that f prime is greater than 0 if x is less than 1 or x is more than 3, and f prime is less than 0 if x is between 1 and 3. And I forgot to include something on this graph, so hold on just a second. So like, let's say this right here is where x is 1, and then this is 3. And like this, see that point right there? That's x is 1, and this point right there is 3. So this is 1 for x, 3 for x, 1 for x, 3 for x. Okay. Well, okay, how can we figure that out? There's no information given. So f of x, no equation is given for this graph, okay? So it's like not like I could work with the equation or anything. I just have to understand what does it mean if the derivative is positive versus negative. F prime greater than 0, positive. F prime less than 0, negative. Okay. Well, let's go back to the top here and talk about what that would tell us. So slope as a concept, if you measure something, whatever it is, at a point on a curve or of a line, if the line is going up and to the right, it has a positive slope. If it's going down and to the right, negative. And if it's flat, the slope is 0. So we'll have to extend that to the curve at large, all right? So what I would say about it if I was describing this is I'd say it this way. So do you see how, like, if I could imagine this curve as a bunch of perfectly straight sections of line that are blended together to form that broader picture of a curve, I would say the slope here in this entire section is positive, right? Because every one of these little lines that I could envision join together and make up that curve are all going up and to the right. So the slope of these individual lines is like that. And so the derivative by extension is positive, okay? So f prime x right here is greater than 0, at least until you get to that point. And then what happens? Well, then the little lines that join together to give the illusion of this curve, then they're slanted down and to the right. So like I'd say like from this point to this point, f prime is less than 0. It's negative, okay? And then after we reach that point, it turns around and rises again. Okay, so f prime here is positive again. So we're like positive slope, then it turns around at this point, negative slope, then it turns around again at this point, positive slope. Well, it'd be choice A then. Okay, my answer, final answer, choice A. Because if x is less than 1, that puts you on this part of the axis, okay, where the derivative is positive. And if x is greater than 3, that puts you on this part of the axis, corresponding to this part of the curve, where again the derivative is positive. But between 1 and 3, that puts you on this part of the curve where the derivative is negative. That will make it choice A. It can't be the other one, even though we haven't looked at it. But the other one is backwards, okay? Here, like, until you get to that point, the derivative is negative. Here in the middle, between this point and that point, the curve is rising, so the derivative is positive. And then from here to the right, from 3 onward, the derivative is negative. Again, why is that? Because the curve's falling, it's going down and to the right, and that's exactly opposite of what we were looking for to choose the graph that has a derivative with these features. Okay? All right. Now, so that's my last problem, what I wanted to show you to tie all the concepts together. Probably do for this assignment that I have in mind with this video, one more video to wrap it all up, and then we'll be ready for the test and the quiz after that.